Hello, this is Mr. McGovern and welcome to the second video in the Energy and Work series. In the last video I talked about energy being useful because we can just look at before an interaction and after its interaction and ignore the complicated bits that happen in the middle. Springs uncompressing or springs unstretching are complicated when it comes to physics. I'm going to prove that to you now, and so that's why we use energy. So we're going to talk about these springs and why they're complicated. So we've got two types of springs. We've got compression springs, are the pictures on the top. They are springs that can be squashed and are used in all sorts of applications. And then we have extension springs. They are springs that are stretched, and then when let go, that they go back to their normal size. The good thing about both the compression and the extension springs are they follow the same physics laws. So we're only going to look at the physics laws for the extension springs, but the same rules apply to the compression springs as well. Okay, so Hooke's law is the name of the experiment that finds out the physics involved here. And the way we do that is we get an extension spring and we hang a mass off it. And what we find is that spring extends. It seems to get longer, as in the picture. If we hang more masses, it extends even more. And so the question is that we can do, and we do this in class, what's the relationship between the force applied, so that's the force of gravity caused by those masses, and how much that spring extends. So we plot this on a graph, and I've just chosen, because it's the way that the equation sits at the end, force to be on the y-axis and extension to be on the x-axis, and I plot my points for this, and it looks something like this. And it looks linear to me. It looks like there's a linear relationship between the two, so I can put a line of best fit, and with that line of best fit, I can find the gradient for it. So the gradient, when I end up working out, is something called the spring constant, and it has a symbol K. The spring constant explains how stretchy the spring is. A larger spring constant is a stronger spring, and a smaller spring constant is sort of a weaker spring. It doesn't require as much force to stretch it out. So you can get an equation from that, because we'll go over y-axis and x-axis and a gradient. So force is equal to the spring constant K times the extension, which is your change in position. So that's the equation I found. However, the equation they give you in the formula sheet looks slightly different. So the two parts that are different is there's a negative in there, and instead of a change in x, a delta x is just x. So let's talk about both of those things. The first is the x. So on the picture on the right here, I've added a coordinate system. I've chosen when the spring is unstretched. I've said that's my origin, my 0 point, and I'm going to call downwards positive. So any of those springs that get stretched, instead of talking about a change in x, because my starting value is always 0, it's just the position it gets to. So that's why I can happily change the change in x just to x. Where does the negative come from? Well, what we're actually looking at is we're looking at the forces on this mass. So I've put two forces there. When it's just hanging there balanced, those forces are balanced. The downwards one is obviously the force of gravity on the mass by the Earth, and the upwards one, to hold the mass in place, is the tension force on the mass by the spring. And you'll notice that the force by the spring is in the upwards direction, which according to our coordinate system on the left there is negative. So the force applied by the spring is in the opposite direction to the way it got stretched, and that's what the negative means. It means that the masses are put on, they pull it down in the positive direction, the spring is trying to apply a force in the negative direction. So this negative means that F in the equation is the force the spring applies, and it's always the opposite direction to what it's been stretched. Okay, what does this all got to do with energy? So we've got this equation, force equals negative spring constant times x, and what that tells us is that it depends on how stretched the spring is to what that force is. So the force applied by the spring changes depending on how extended it is. Now, we haven't had to deal with changing forces in a situation in level 2, and to some degree in level 3 as well. It's very complicated, and you have to start using something called calculus to work through that. Here's an example of another spring, a compression spring. So a ball is pushed against it, and then we let go and the ball fires away. Now, as the spring starts uncompressing, every millimetre that it uncompresses a little bit, the force it applies to that ball is going to change, every single millimetre. And so that's a very, very complicated situation to have to work through. It's easier to deal with just the before and afterwards. Before being the ball's compressed against it, and afterwards the ball's fired off. And that's what energy is. Instead of having to deal with the things that happen in the middle, energy is really useful for looking at situations when we only want to look at the before and the after. And so it's easier to use energy to analyze springs. We can still use Hooke's law, F equals negative kx, if we just want to look at something that's not moving, just hanging there. But certainly if a spring uncompresses, we certainly want to use energy. There will be a formula for the energy of the spring, but I'm going to give it to you later after I've done the energy bar charts and I introduce all the formulas at the same time.